Welcome to the Planckatron and other Planck-related things explained by me, Zachary Giofku. The Planck scale, the Planck mass, the Planck constant, what are these things? Are they the same thing? Are they different? Does Max Planck point and laugh at us who don't know what the differences between his measurements are? Am I ripping off CGP Grey way too much already? Who knows the answers to these questions? I do, and I'm going to explain them to you right now. In short, the Planckatron is a supermassive particle accelerator that accelerates particles to the Planck scale, 1.22 times 10 to the power of 19 giga-electron volts. But before we go into detail on the Planckatron itself, let's learn about the Planck scale. The Planck scale in particle physics is a very high energy state where the four fundamental forces supposedly change significance. It corresponds with the Planck mass in the mass energy equivalence. The Planck mass is measured in Planck units, which are related to the Planck constant, a much more scientific and useful to physics concept than a certain other constant. There's also Planck time and Planck length, which in some way or another relate to all the other Planck things. As mentioned before, the Planckatron accelerates particles to 1.22 times 10 to the power of 19 giga-electron volts, or 12 quintillion 200 quadrillion giga-electron volts. In comparison, the Large Hadron Collider accelerates particles to 7 times 10 to the power of 12 electron volts, or 7 trillion electron volts, or 7,000 giga-electron volts, which is less than a fraction of a percentage of the energy the Planckatron will theoretically accelerate particles to. Do a little maths and you find out that if the circumference of the Large Hadron Collider is 27 kilometers, to accelerate particles to the Planck scale, the circumference of a Planckatron would need to be roughly 300 light years, which, for comparison, would make a theoretical Planckatron about the size of the Milky Way galaxy. So what's the point of this? Why hypothesize a collider that is far too big for anyone's good? Apart from being super fun to conceptualize, in theory, when particles reach the Planck scale, gravity becomes strong. If you recall back to the start of the video, I mentioned that at the Planck scale, the fundamental force's prominence alters. As we all know, gravity is the weakest of the forces. This is no longer the case at such a high energy state. Because gravity is not prominent at the quantum level, where it is superseded by electromagnetism than the strong and weak nuclear forces, it becoming significantly more noticeable at such a small scale is a huge point. Of course, we can't ever be sure of this until we do indeed build a giant collider and test it. Come on, science. So in conclusion, the Planckatron is too big to build or even think of building. The Planck scale could be completely false. We don't know, as it's a far higher energy state than anything we've ever observed on Earth before. There's too many Planck things for anyone's good, and as always, thanks for watching.